Formula for volume and surface area of sphere using cell method, disk method, and ice cream method. I'll tell you what these are. This might look weird now. And also the surface area using ring method and surface area element method. So we'll just go, just chill and just try to understand. Okay. Now first of all, cell method. Basically, what cell is regarding cell, this is just a circular hollow cell, right? Circular hollow cell. It's actually a hollow cell that would actually be in 3D, like it will be enclosed, right? Like just like a football, or a soccer ball. That's a cell. Yeah, and disk is basically just a kind of floppy disk, right? It's a 2D shape. This is disk. There might not be hole. Yeah, and ice cream is basically just ice cream. Ice cream is basically a combination of a cone and a sphere on top, right? And the ring is a ring, just a ring. And there's just a boundary. There's no surface. And surface area element is just kind of a surface area element just like this. We will later discuss on it. Okay, now let's go. We'll start with disk method. Okay, now we want to find the volume, right? So using disk method, I'll explain. So let's say we have a sphere, right? Now what I want to do is, first of all, we will just consider, let's say, the half sphere. We will not consider this half. Yeah, and we will try to find the value of half sphere and then multiply by 2. Now what we will do is, as our x coordinate goes from 0 to r, we will just try to sum up all the small volumes. Like basically this area of this area of this 2D circle times a small gap. Again, the area of this 2D circle times a small gap. That will just be a small volume, right? That will just be this one. This one will just be a small volume, right? I mean, this one, and then something like this. This is our circle, and this is our small d change in x direction dx. This is our this circle. The area of the circle is basically just pi y square, right? Because the radius will just be the y coordinate, right? If this is the origin, this is the x coordinate system and this is the y coordinate system, right? And let's say if this curve, yeah, let's say this is in a 2 dimension, right? If this curve is in 2 dimension and y is equals to f of x, will give this curve of 2 dimension, right? Then yeah, so every this point will just be x y, right? x1 y1 x2 y2. So yeah, so basically now what we can do is, with this 2 dimension curve, if I'm trying to find pi y square, I will get the area of this circle, which basically comes out of the screen and goes in of the screen, right? So yeah, so what we are going to do is just integrate from 0 to r of pi y square, this circle, times dx from 0 to r. So this is the small, this volume element, and this is added all of this circle with the small gap over here. This one, again, this one with the small, I mean, you understand, right? Like all these small volumes are being added with this element, and yeah, so total we get this entire volume of the half sphere. So this is the disk method. And using this, now we know that if this is will basically be a circle, right? So that will be given by y square plus x square is equals to our radius is r square. So y square will just be r square minus x square, right? And yeah, we just want the y to be this upper half. Yeah, we just want the I to be upper half, so that this, with using this y length, if we find pi y square, it will just revolve around with this length. This will give us an area of this circle, right? So yeah, we do know that y square is just r square minus x square. Substitute pi times y square is r square minus x square dx, and we get 0 to r pi r square dx minus 0 to r pi x square dx. This is just pi r cube minus this is pi x cube by 3 from 0 to r pi r cube minus this is pi r cube by 3. So wait, this is not the desired result, right? Did I do any mistake? Yes, this is the desired result, because now this is 2 by 3 pi r cube, but this is just this is just the area volume of half sphere, right? And now for volume of full sphere, that will just be 2 times 2 by 3 pi r cube. So that's 4 by 3 pi r cube, which is the formula for the volume of sphere. So this is how the first method works. The second method works, the disk method. Now, I hope you understood this. We just added all these small volumes like this, and yeah, using and adding all these small volumes, we got the volume formula, and then also we multiply by 2 to get the volume of entire sphere. Now let's go to cell method. In cell method, we are going to add the small soccer ball or football like elements. So basically a sphere is a combination of different layers, okay, this is also, let's say, a hollow sphere. Again, there's another hollow sphere, there's another hollow sphere, there's another hollow sphere, let's center, another hollow sphere. Yeah, so we are going to add the volume of the volume of the layers. So if hollow sphere is like this, yeah, we are going to add the volume of this of the small layer of hollow sphere, right? And if we add these things, if we just add all the layers, we'll get the entire volume of the solid sphere, right? Because all the small like layers volume is being added. So this is being added, and this is being added again, this is being added, this is being added. So all the small layers volume is being added. So using that, we can get the entire volume of big sphere, right? So we will use that. Now for let's say in x coordinate, we are going to go again from 0 to r, and what we want is, let's say for a certain over here, while we are at distance x from the O, so the volume of the small the football like thing, the cell, will just be okay. For this one, we need to know the formula for the area of the surface, the surface area of sphere. We don't need to know that for this one, and we know that we don't yet know, because we are going to derive it in the next section. But yeah, let's consider we know. Just like how we consider that we know the formula for area of circle, let's consider we know the formula for the area of the surface area of sphere. In the next method, in the ice cream method, we will assume that we don't, even if we don't know anything, we are going to find it. But in these two methods, there are some assumptions, right? In this one also, we are not going to assume that we know anything. Also over here, we will assume we don't know anything, right? But yeah, for now, let's say we know. So okay, we know that this small volume of the cell will just be the outer surface area, right? The outer surface area times a small dx element, which is going to give it the volume. Total perimeter, the outer surface area times the small dr is going to give us this volume of the outer shell, right? So our the volume element will just be 4 pi x square times dx. This will be a volume element. So yeah, now using that we are going to add all the volume elements from 0 to r, right? So for every radius we are going to find the volume element, this volume element for everyone. So if we do that, if we go from 0 to r adding every volume elements, we are going to get the volume of sphere, right? Volume of sphere. And so that will just be 4 pi times x squared dx is just x cubed by 3 from 0 to r. That gives us 4 by 3 pi r cube minus 0 cube. So that's 4 by 3 pi r cube. So this was pretty simple because we already used another standard formula, right? Okay. Now let's go to a real one, the real thing. Now for this you need to know some concepts of spherical coordinates. Okay, you do need to know the ice cream method, right? Ice cream, yeah. You do need to know some of the ideas of the spherical coordinates. So in spherical coordinate system, how this works is, so yeah, let's say we are in 3D. Okay, so let's say we are in 3D, right? This is I think it's better if I do it in a different way, I guess. No, let's say this is fine. Okay, let's say if you are in 3D, right? Now in spherical coordinate system, every point in the 3D, let's say some point over here, this is basically just above. Okay, so if it's xyz coordinate system, we will describe it by its x coordinate, its y coordinate, and its z coordinate, right? So corresponding to, I'm sorry. So in normal Cartesian coordinate system, we will just look for this point. We'll basically look at what x coordinate this is. So this basically belongs to over here. This so belongs to this x coordinate, right? And this belongs to this y coordinate and this z coordinate, right? And now in the spherical coordinate system, the location of any point is determined in the following way. So for any point over here, we will basically try to see 3 different factors. First of all, its length from the center, right, which is called as rho, and its angle from the z-axis, which is called phi. And if we project this to the xy plane, right? Oh, this is supposed to be xy plane, not x. If we project this to the xy plane, the angle made with the x-axis. Okay, so for the angle made with the x-axis is in this case theta, right? So this theta. So this coordinate will just be named as rho phi theta. Is it the good order? I guess it's rho theta phi. I'm sorry. Yeah, rho. I don't know. Anything, it doesn't matter anyway. Theta phi. Yeah. And these 3 components will like uniquely define any point on this 3D surface, 3D space. Any point on 3D space can be uniquely defined using these 3 coordinates, right? So phi is angle from the z-axis, rho is distance from origin, and theta is angle with respect to x-axis if we project it down. Now, yeah, so this is how a spherical coordinate system works, and using these 3, if you know these 3 values, we can like strictly find all the coordinates, because if you just use some trigonometry, you will know that z coordinate is just rho times cos theta, rho times cos phi, right? And yeah, if this length be r, you see that r is just rho times sine phi, right? And now x coordinate is just r times cos theta, and since r is rho sine phi, this will be rho times sine phi times cos theta. And since y coordinate is just r times sine theta, that will be rho times sine phi sine theta. So you see that this basically these three components will basically define all the x, y, and z coordinates. So yeah, obviously it will define every point on 3D space. Now, now to use this method, now also we need to. So we want to find a volume of a sphere, right? So notice that. Now notice that. Now you need to notice a few things if you are just beginner. So yeah, obviously don't just try to understand it. It will not be that hard. Now notice that when when like okay, let's say for a given row, for a given this length from origin, for a given length from origin, let's say this length. Now while this angle rho goes from 0 to pi, right, and this angle with x-axis, this angle theta goes from 0 to 2 pi. Yeah, okay, so this line, if it's basically, I mean this point actually, if it's going from z-axis to downwards and also rotating throughout the axis, you will see that this is basically generating a hollow sphere, right? This is basically generating a hollow sphere. And again, in that, if this row is if all these rows from 0 to row value, from 0 to the row value, for all these rows, if you are just rotating it from positive z to negative z, as well as throughout the z axis, I mean rotating throughout the z axis using angle from 0 to 2 pi, you see that a sphere will be generated, right? You see that a sphere will be generated. I mean, if you just allow the row to be row to go from 0 to pi, theta to go from 0 to 2 pi, and rho to go from 0 to the length, I don't know, the just the radius of a sphere, let's say r, where r is the radius of a sphere. If you allow that, you will see that a sphere will be generated, right? Yeah, so we see that a sphere will be generated, and yeah, and that's a really good observation. Okay, now using this observation, we will basically try to find the volume of the sphere. Now from this observation, notice that our volume will just be, if we integrate, if we allow the phi to be go from 0 to phi and theta. So let's first I'll write like this. Let these restrictions define our domain D. Then volume will just be domain D or E in this case, because there are three things. In a 3D space, we define domain as E. I don't know why. If we define it, we can define that in this domain, if we just integrate the dv, we will get our volume, right? Yeah, and notice that this is this whole thing that I'm describing is basically for xyz coordinate system, right? So if the domains are these same domain, but if these are written in terms of x, y, z coordinates, z code in the x or z coordinate system, only then we can write it as dx, dy, dz, and also these whole thing need to be in the Cartesian coordinate form. But if we want to write it as, let's say, d rho d phi d theta in terms of dx, dy, dz, we will also need some scaling elements that scale this area to the x, y, z, to this volume. I mean the volume in this parametric system to the volume in the other parametric system. We will need some scaling elements, right? So that I can also write over here, and if we find that scaling element, we can write over here 0 to pi, 0 to 2 pi, and Okay, this should be theta. The second one should be theta cos. No, it doesn't matter, but wait. I can also write third one as theta, but then this one should be go from doing from 0 to pi. This is phi, so this goes from 0 to phi. This is rho, so this goes from 0 to radius r, right? And now the scaling element, we can find that using Jacobian determinant, which is just the ratio of the change in areas into coordinate system, right? If you want to find that, the Jacobian is basically written like this. This is being long, but yeah, I'm just trying to explain the things in a better way. I hope I am. So if you want to, basically Jacobian helps us to transform from, okay, so this is called the Jacobian, the partial xyz by partial rho phi theta d rho d phi d theta, and this Jacobian, this is called Jacobian, the ratio, and this is calculated by dx by d phi dy by d, this is rho, sorry, dz by d rho dx by d phi dy by d phi dy, so no, not dy, dz, dz by d phi dx by d partial, it's not d, it's partial, partial y by partial theta, partial g by partial theta. Now what I wanted to do is, we know that x, y, z are these things, right, in terms of theta and phi. Just substitute that and try to find all the partial derivatives, try to compute determinant, and yeah, that's your work. If you do that, you will get rho square sine phi, and then this is d phi d rho d phi d theta. This is our dx dy dz. Okay, now we know the scaling element, right, which is rho square sine pi. Now we just need to integrate. So from 0 to 2 pi, 0 to pi, 0 to r of rho square sine phi d rho d phi d theta. Now we know that if the function are products of the functions, I mean the different input, the different what do I say that independent variables, they are constituting function as product of them, right? So we can basically write them separately. So there's no theta's function, so just 0 to pi theta for phi is sine phi d phi, right, guys? And I noticed that the area from the upper person might cancel the area from lower person due to the negative sign. So I think, so and as a result of cancellation, the area might come 0. So that's why I will just allow the phi to go from 0 to pi by 2, so that all the volume that we get will just be positive volume, and I can multiply this result by 2, right? So that will give me the entire volume. So that's just the idea to yeah, to avoid the answer being 0 and get the actual result. So I'm doing that over here. Okay, and then 0 to r rho square d rho. Now this is 2 times 2 pi. Now this will just be minus cos phi from 0 to pi by 2, so that's just 1, and this is just rho cube by 3, so r cube by 3, and we get the beloved formula 4 by 3 pi r cube, and that's our achievement after this long struggle. 4 by 3 pi r cube. Okay, so we got this one too, right? Phew, we went from the very beginning to the conclusion of formula. This was instead a very this is almost a crash course, from introducing the spherical coordinates to introducing the Jacobian to evaluating the integral, triple integral. This was a lot of things. But I do hope that even if you had never known about the spherical coordinates, you might have somewhat got the idea, though not completely understood, but you should have somewhat got the idea of how this is working, right? And that's the aim of my channel too. This is to give you the exposure to different interesting things in maths. Okay, so now after all these things, after all the volume computation, now let's go to the surface area computation. First of all, ring method. Ring method is pretty easy, but this one can be a little harder. Okay, now ring method. Now in a ring method, just like the disk method, what we are going to do is, So basically this is our, let's say, coordinate system, right? And this is 0, this is, let's say, the r. And while we are going from 0 to r, we are basically going to so let's say this is our like 2D circle, right? This is our 2D circle, which is defined by y square plus x square is equals to r square, right? So in this 2D circle, for every y, now we are going to find this circumference of this circle multiplied by the small dl element. This is small length. So what we are doing is basically to the 2 pi r, to this circumference of circle, we multiply by dl, so that we will get this small surface area. Now initially we calculated the inside volume by pi r square times dx, but now we are calculating this small surface area of the outside portion, this small surface area of outside portion, by multiplying this 2 pi r by this length, 2 pi r times small length dl, right? So that's our aim for this one. So while going in, we'll just multiply by 2 later on to get the entire surface area. So while going from 0 to r, we will just multiply. Now in this case, this will be the y, right? For different, there are different y's, y is changing, so we'll just write y. So 2 pi y, and notice that in the boundary, I will write not just 0 to r, I will also write while x goes from 0 to x goes to r, to avoid some confusion, because right now our this differential element is in terms of L, right? So if I write just 0 to r, it might seem like our this L is going from 0 to r, but that's not the case. The L is not going from 0 to r, it's the x that's going from 0 to r, right? Now yeah, this gives us the small surface area. Now we need to add all these surface areas, this 2 pi r times dl, right? All these outer surface areas, and then yeah, add them up and give the entire surface area of the half sphere, right? So yeah, and now notice that for this small dl, so over here there's a small dl, right? So okay, now for dl, notice that what you can do is this dl is made from small, the dl is made from small dx and small dy, right? Yeah. So what will happen is just dl square will just be dy square plus dx square. Whoa, Pythagoras theorem comes here in a surprising way, right? Now after that, dl will just be square root of dy square plus dx square. That's an interesting observation. Yeah. So this will just be integral from x equals to 0 to x equals to r, 2 pi y dl is just square root of dy square plus dx square. Now since the limits is in terms of x, we will try to bring the x outside. What you can do is just divide this by dx square and also write dx over here. Notice that this is just square root of dx square, right? So that just cancels out. I don't need to write square root of dx square, yeah? Now this is just from x equals to 0 to x equals to r, 2 pi y 1 plus dy by dx whole square times dx. Okay. Now y, we know that y is just okay, what's y? Y is basically just square root of r square minus x square, right? Yeah. So from x equals to 0 to x is equals to r, 2 pi square root of x square, sorry, r square minus x square, r square minus x square. And now what is dy by dx? If y is square root of r square minus x square, dy by dx is just 1 by 2 root r square minus x square times minus 2x, right? Guys, don't be afraid of this. This will just cancel out in a second. So yeah, don't be afraid. X is equals to 0 to x is equals to r. Now we don't need to write this because we already our differential is in terms of x, so yeah, it will be understood by default. Yeah, from 0 to r, 2 pi square root of r square minus x square root of 1 plus, this is for x square. Oh wow, yeah, 2 cancels out, not, so we don't need this for x4, we don't need this. Okay, this is x square by r square minus x square times dx. This is integral from 0 to r, 2 pi square root of r square minus x square. Now this is just square root of r square minus x square plus x square by r square minus x square dx. Note that even though there is a lot of algebra, it's actually pretty easy, right? 2 pi root r square minus x square. Now this is just r by square root of r square minus x square times dx. These to cancel out. So we have 0 to r, 2 pi r dx. Really? Okay, 2 pi r. Wow, if I had just used the polar coordinate system, it would have been so easy, right? Really? No, I think, can there be r? I think we have made some mistakes, right? Because this shouldn't have. I don't know. Let's go on. Maths should work. Okay, so this is 2 pi r times r. This is 2 pi r square. Okay, so now if I multiply it by 2, it works, right? Like we got the surface area to be 2 pi r square. Now for the entire surface area, total surface area, just multiply it by 2. So 2 times 2 pi r square, so that's 4 pi r square, which is the formula for surface area of a sphere. But guys, now I'm just wondering if this simplified form has any meaning. While going from 0 to r, just multiply 2 pi r with dx. Does that make sense? 2 pi r is basically just this entire, the perimeter of entire circle, and then dx. We cannot do that, right? While going from 0 to r, we cannot just always multiply with this big circle, right? The circle gets smaller and smaller. But how is this working? While going from 0 to r, 2 pi r is just a constant. Maybe the fact that this dl is larger will just compensate the decrease in the circle, right? So that's an interesting observation actually. The fact that at every point 2 pi r dx is actually equals to 2 pi y dl. So that means at every point r dx will be equals to y dl, and r dx same everywhere, so y dl is actually conserved. Whoa, y dl is actually conserved. That's a good observation, right? So at every point this y value times this dl is always conserved, or that's always same, and that's actually equals to rdx, because yeah, over here it was rdx, right? Wow. Okay, if we had already known that at the every point of this sphere, at the every point of this sphere, if this we had known that this y times dx, if y times dl actually, sorry, y times this dl is conserved, we know that at this very point this is just r and dl is just straight, just dx, right? So yeah, we could have just used that at this very point it's actually just r dx, and then we could have written 2 pi r dx over here, and then easily integrated. This one is interesting observation, guys. Try to remember that in a sphere, the y times dx is all dl is always in. Okay. Yeah. Now, yeah. Let's not get deep about this. We have something else to do as well, right? Now, finding surface area using surface area element method, right? Again, now for this one, we'll just get back to the spherical coordinates because that's easier. Now, what happens is, what happens is, now, okay, let's say if this coordinate system was in terms of, again, these three elements, rho, theta, phi. Now, we are trying to see, let's say if I just made this as coordinate system, but yeah, this thing is in terms of these three coordinates. Now we are trying to see this small surface area element uh, from from the domain where it's basically d rho, d theta, d phi. Or okay, now first, I mean, for the surface area, the rho is constant, rho is fixed, right? Rho is just the big the r itself, the radius of sphere itself. Now for a small this d theta, d phi, this over here, we'll try to find surface area element in terms of the d theta times d rho, this surface area element for every area. We'll try to, for every domain, we'll try to see how this surface area element changes. And then if you know the surface area element, we will try to find the entire surface area by going through the entire like domain, this entire domain where we have surface area above and down. We'll just first find the surface area above the sphere and then down the sphere. Okay, so that's the idea. So yeah, so first of all, we know that this sphere can be parameterized in terms of the, I mean, the boundary of the sphere, the boundary of sphere can be parameterized as, okay, in terms of the theta and phi, yeah, and the x coordinate of the x coordinate in the boundary of sphere, x coordinate in the surface of sphere. I mean, the boundary means just the surface, right? X coordinate will just be rho. Rho is just a constant, right? I mean, let me write r actually, yeah, because r is a fixed value. Rho seems like changing like a variable, right? This will just be r, and then sine phi cos theta, and then r sine phi sine theta, and then r cos phi. I have already shown this in the spherical coordinate system, right? Yeah, I've already shown this over here. Yeah. Now using that, what I will try to find is, I will try to find the partial change in r due to theta, partial change in r due to phi, and then we will try to see how this partial change in r and theta, the area covered by the partial change in r and theta. I mean, so in this surface, what's the area covered by these two partial changes by in theta and phi? This basically this parallelogram, right? And once we know this, we'll just try to find over the entire surface the ds. We'll just try to integrate the ds, small ds element over entire surface domain, which is the surface domain is basically the same thing, the phi going from 0 to pi by 2, theta going from 0 to 2 pi, and then rho is rho itself, right? We will find the upper surface area and multiply by 2. So yeah, we will use that technique again. And now we are just this whole thing we are doing is for ds, and we will see that ds will just be the area parallelogram given by small change in this surface area parameterization by theta and phi, this one multiplied by d rho d phi. So basically over a small rectangle over here in the domain. So yeah, the This is just the scalar that gives us how much area in the actual surface has been changed. It might have seem a bit a lot of big, but yeah, just try to come up with this. You will get the idea. Okay, now this is just minus r sine phi sine theta, and this is just r sine phi cos theta. This is minus r sine phi, and this is again. I'm doing right, huh? Yeah, I'm doing right. Okay, no, and this will actually be 0 because this is in terms of theta, so this will just be 0. In terms of phi, this is r cos phi cos theta, and then these are vectors, okay guys, and then and then to find the partial derivatives, I guess you guys know that we need to be doing it part by part, right, for vector functions. Yeah, I guess you know that. And yeah, and now this is r cos phi cosine theta, and I did not acknowledge the fact that the parameterization, how it's done. I just assumed that you know about how this is x coordinate, this is y, that's z coordinate. I guess you know that, right? And yeah, okay, fine. Now this is minus r sine phi. Now guys, try to find this vector, and again also try to find, after finding the vector, try to find its modulus. I already know that, so I will just write directly. That will be r square sine phi. Try to find that, and this is not a coincidence that this is same as what it was earlier. Yeah. Now let's try to integrate. Now the total surface area will be 2 times surface area of the upper half, right? And so yeah, 2 times for surface area. The domain will be phi going from 0 to pi by 2, theta going from 0 to 2 pi, and this cross product is just r square sine phi times d phi d theta, right? So this is now 2 times r square will come out as it is, right? And then sine phi, 0 to pi by 2 of sine phi times 0 to 2 pi of d theta, right? And this will just be 1, and that will just be 2 pi. So yeah guys, we get the formula for pi r square for the surface area of the sphere. So this is done too guys. So yeah, this was a long video, but this had a lot of information, right? We found volume using cell method, disk method, ice cream method, as well as, and the reason it's called ice cream method is, try to Google it. Yeah, it's not too hard, because if we had a small change in phi, just a small change in theta, and a small change in rho, that will give ice cream actually. If it was not the entire change, it becomes a sphere, right? This goes big and big. If phi is increased, this becomes a sphere, but if phi is just a little quantity, this becomes ice cream. So it's called ice cream. Yeah. And yeah, and we also went over ring method, surface area method, and we found all of these things. So that was awesome guys. I enjoyed this session. I enjoyed doing all these things. First of all, going through the cell method, disk method, and then ice cream method, and also later on going through the ring method, and then finally coming back to this surface area element method. So yeah, I did enjoy. Hope you enjoyed too. Hope you learned a lot. Hope it was helpful for you. Thanks for watching, and look forward to seeing you in the upcoming video.